molecular shape. The derivatives of electron domains of trigonal bipyramidal. The axial lone pair does not occur, and I've stated that earlier. We remove, when we're going to have an electron cloud, remove it from the equatorial position. And again, that's important just to minimize electron repulsive forces. If I place one on top, we're not alleviating as much crowding as if I removed it from the side. So the first to be removed would be one of the equatorial, then a second, and then a third. So again, remove from the equatorial positions when we're creating the derivatives of the 5 electron domains known as trigonal bipyramidal. A closer look at seesaw. In a seesaw-shaped, this is interesting, they've removed one, but here I would flip it this way to see what they've done. If this is a molecule, it was SF5, sulfur pentafluoride. When I remove to go to a seesaw, I take an equatorial position. So I would not take off either the axial, but always remove one from the equatorial position to create a seesaw. And literally when we build these, it's like having a leg. The sulfur atom, and these two would just be sitting flat on the table. I can place a person here, and you can go up and down like a seesaw would. And that's where it gets its name from, a seesaw shape. The T-shaped of this particular electron domain is still a trigonal bipyramidal, 1, 2, 3, 4, 5 electron domains, but notice I've removed 2 then from the equatorial position, and it now looks like a T-shape, bond angle of 90 degrees in either direction. So here's the letter T when I make this molecular shape. T-shaped has 5 electron domains, 2 non-bonded, 3 bonded back to the central atom. Bond angle here, just 90 degrees. 180 from top to bottom, 90 degrees here. Here's an example of a T-shaped molecule, 5 electron domains, 3 of them bonded to fluorine, 2 non-bonded pair, the T-shaped giving us a linear fashion here, and straight down. So I can see the letter T with that particular shape. If it's linear, we had 3 electron domains that are unbonded. And again, all 3 are taken from the equatorial position, giving us a 180 degree between the 2 that are left in the axial position. Xenon difluoride would be an example here. Moving on to the octahedral electron geometry. Again, on our page, this focus here where we have 6 electron domains. If all 6 are bonded, we can see that the electron domain geometry and the molecular geometry would match to be octahedral. If I remove one of the bonded pair, we get square pyramidal. And if I remove 2 of the bonded pair, we get a square planar. Let's take a peek. When there are 6 electron groups around the central atom, and some are lone pairs, even number lone pairs will take a position opposite the previous lone pair. When there are 6 electron groups around the central atom, and one is a lone pair, the resulting is a square pyramid. The bond angles between axial and equatorial position is less than 90. Let's take a peek of what they just said. The first one to be removed is an axial position. The bond angle in any direction, recall, is 90 degrees. If this is an electron pair that's not bonded, that's a big cloud, and so they're saying it's going to push those other to be a little less than the 90 degrees. A moment ago up here, just to stress, the trigonal bipyramidal, we always remove from the equatorial position. Down here, the octahedral, if I remove one, the second one is going to go the exact opposite location. Now remember, this particular molecule is completely symmetrical. So when I say axial, I could flip it. Now, I mean, truly, they're the corners of an octahedron. Wherever I take one off, the second one to be removed goes in the exact opposite. So just follow through the straight line. Here's a straight line, here's a straight line, here's a straight line. That's an octahedron. Whatever one you remove first to create a square pyramidal, the second one that's removed is the exact opposite end of that same line. It really doesn't matter which one you choose to remove because all of these are created equal. There are no differences in bond angles as there were up here in the 5-electron domain. So take off any one to go from octahedron to square pyramidal, but when you remove a second one, make sure that it's exactly the opposite. In other words, it's going to be the other atom from the same straight line in the octahedron. And that's what this slide is really saying. Bond angles between axial and equatorial are all 90 degrees. So if you remove one electron pair to create what's called the square pyramidal, the second will create a square planar shape. Square pyramidal, I still have a square around the around the equatorial position with a pyramid coming to the top. I can see a triangle up here. Square planar, all I have left is the square around the equatorial position. Take a peek at some models here. Octahedron electron geometry shows 6 electron pairs. If one of them is non-bonded, I can take off any of them and create a non-bonded pair. This is coming from the axial position. The second one must be removed then from the opposite of the straight line. So here's the equator. All of those stay intact. If I remove one, the electron domain is octahedral, molecular geometry, square pyramidal. If I take off 2, I take off the one that is in the same straight line. Xenon tetrafluoride shows 2 electron domains that are unbonded. Molecular geometry is called octahedral. Molecular geometry now shows a square planar molecular geometry. I can see the square as I build these. Here finally in our text is what I handed you earlier, putting all of these kind of in one spot. I start with the linear electron domain, trigonal planar electron domain, tetrahedral electron domain. And again, a little later on in your text, you'll see the number 5 and number 6, the trigonal bipyramidal and octahedral. But finally on slide 46, they're giving you this half of what I gave you earlier from a different text, all in one spot with bond angles, molecular geometry, and electron domain geometry. Probably a handier tool, I think, than the one in our text. Alrighty. Predicting the shapes around central atoms. If we draw the Lewis structure first, and that's a chapter 9 skill, we determine the number of electron groups around the central atom, classify each electron as either bonded or non-bonded, and simply count. Remember that multiple bonds count as one group. We use our table called the Vesper table to determine the shape and the bond angles. So it's as easy as drawing, but that in there lies the rub, I would imagine. How good are we at drawing our Lewis dot structures from chapter 9? Let's suppose we want to draw a molecule, phosphorus trichloride, PCl3. We're to draw the Lewis dot structure first, and all we've done is tabulated how many valence electrons we have to work with. So step 1, phosphorus, it's P, who lives in group 5A, has 5 valence electrons. Chlorine lives in group 7A, so it has 7 valence electrons, but there's 3 of them there. 21 plus 5 gives us a total of 26 valence electrons. So by the time I'm done drawing, I better be able to account for 26 electrons. Determine the number of electron groups around the central atom. And again, the central atom between phosphorus and chlorine, think symmetry. I always put the one I have just one of, place it in the center.